Okay, good to have you here today. It's kind of a cold, wet, rainy morning, but it's good to have you here. Dad, the little birds are here. I know, 16 of them. 16, I know. I'm naming them. Okay, that's exciting. What are they doing? They're eating, they're drinking, they're pooping, they're doing everything. Oh, that is exciting. The first class doesn't know about them yet. Well, tell them. Well, yeah, we got 16 little chicks, and I'll show you. Uh, I'll show you Friday in class, and remind me if I don't show you, but I'll try to remember. They're great. They're super great. Yeah, they are great, and they're doing real well so far. They're a little fragile when they're little. They came in the mail. Yeah, I know, like in an envelope. No, they came in a little box, but they are doing fine. Can I go see them? I want to go see them. Sure, you can go, and don't worry about missing class. Okay, I won't. Yeah, but I need Ohm. Ohm isn't here yet. He's always late. Yeah, I know he's always late, but he'll be here in time, I'm pretty sure. There are a couple things I wanted to talk about today. The first one has to do with partial derivatives. And this is not a big deal, but I wanted to point it out. That usually when we take partial derivatives, at least for examples, we have an equation. It can be a little complicated. You can have some products. But when you take the partial derivative of, say, z with respect to x, you just go through and treat the y as a constant and take the derivatives. And this is how it always works, but it looks a little different if the variables are not x, y's, and z's. So I gave you a couple of these in the book, I think 84 and 83, something like this. One of them, a simple one, is the kinetic energy equation. Kinetic energy of something in motion, like me chasing my brother, is 1/2 mv squared. Mv is the speed or the velocity, is why the v is there. And this is written in function form. So k is a function of m and v. So finding these two values is pretty easy. It's just like the ones we were doing. You don't normally think of m as a variable here, the mass, but we can take the derivative, say, of m with respect to v. And I thought I'd show how to do this, because using implicit differentiation is easier than the solving for m. In this case, you can solve for m, but you can do this implicitly using this equation. The derivative of k is 0 with respect to v, because v is the variable. On the other side, we have a product, 1/2 m and v squared, so that's the product rule. The derivative of the first is 1/2 times what we're looking for, the derivative of m with respect to v, times the second, plus the first, 1/2 m, times the derivative of v squared, which is 2v. So this gives you an equation that you can solve for the quantity that you want. So the partial derivative of m with respect to v is equal to minus mv divided by times 2 divided by v squared. The v equals 0 case is probably a special case, so you can reduce. So you get minus 2m over v. So this is all I wanted to show you about partial derivatives. But a lot of interesting mathematics comes out of working with relative rates of change of some variables relative to others. So that's it for partial derivatives. And now I need Ohm, because what I want to talk about next is tangents to surfaces. So what kind of things are tangent to surfaces? And Ohm doesn't particularly like this, but a great surface is his shell. Ohm's shell is a surface. I hate it. I hate this. Yeah, I know, Ohm, but it's okay. It will work fine. Okay, just don't put chalk on my shell. Well, I need to put chalk on your shell a little bit anyway. I'll wipe it off. So the reason I put chalk on Ohm's shell is to indicate where I'm going to look at the tangent. The tangent is at a point, so we're going to look at tangents at points. And lines can be tangent to this point, but the actual tangent surface here is not a line. The sort of the maximal tangent surface is a plane. It is the plane that is actually tangent to Ohm's shell right at that point. So when we have a surface, a function of two variables, the tangent to that surface is a plane. So we'll be wanting to look at the plane. We'll also look at tangent lines, and the tangent lines will be the lines that lie in the plane that go through the point of tangency. So any line like that goes to the point of tangency and lies in the tangent plane will be a tangent line. And this extends to higher dimensions as well. Erase the point. Oh, well, yeah, I can erase the point now. It's fine. Thanks. So there we go. Good as new. So thanks a lot, Ohm. Yeah, you're welcome. So let's take a look and see how this works and how to find these things. We looked at tangent planes in this case. So we want equations of tangent planes, and we can look at them in Cartesian form. And the Cartesian form is actually Cartesian graphs. So we're looking at a Cartesian graph, or we can look at a parametric function, in which case we're not looking at the graph, we're looking at the range. And there's a relationship between these two, and it's a relationship that I want to talk about. This is my new chalk. It just came the other day. I've already burned through 3 pieces of it. Ojoromo, it is the best. So a Cartesian graph might be of the form z equals 3x plus 2y plus 8. This is the slope-intercept form of a plane. It's got 2 partial slopes. A slope with respect to x is 3, and a slope with respect to y is 2. And it's got an intercept, a z-intercept, is a number, and it is 8. Now, this is typical. Our book uses x, y's, and z's. More typical mathematically is that the input variables, if it's in function form, are x1 and x2, and the output variable is y. So we have a slope in the x1 direction, a slope in the x2 direction, and a y-intercept. This corresponds more closely to the one-dimensional case. I want to rewrite this a little bit. So y equals the ordered pair 3, 2 times the vector, or dot product with the vector x1, x2 plus 8, or y is equal to the total slope, which is an ordered pair, m, which is the ordered pair m1, mx1, mx2. So this is a ordered pair, or a 1 by 2 matrix. times a vector x plus an intercept b. B is just a number. So such an equation can be written in vector form in exactly the same way as it is in one dimension. But in this case, m is not a single number. It has as many components as does the vector x here. This is a dot product in this case. And when you work this out, you get this exact equation. But this is of the form y equals mx plus b. Linear equations in several variables always have this form, y equals mx plus b. So I wanted to point this out. Now, there also is a relationship between this Cartesian graph and the parametric function for it, and I wanted to point that out. I'm going to erase this and work under the parametric function. So to find the parametric function for this, what we need is a point on. And for the point on, let's use the y-intercept. So if x and y, if x1 and x2 are both 0, then the intercept is 8. So the point on is 0, 0, 8. That's what this y-intercept means. That at the origin, the height will be 8. And we want two directions, dir1 and dir2. These are both vectors. And this is exactly these are the three things you need in order to find a parametric equation for this plane. And for dir1 and dir2, we're going to use the slopes. M sub x1 is 3, and this does mean rise over run. Rise means in the y direction, in the vertical direction, but run, since the domain is the plane, x1, x2 plane, run as a lot of different ways. There's a lot of different directions you can run, but this means run in the x direction. Vector-wise, the x direction is 1 unit in the x1 direction and 0 units in the x2 direction. So go 1 unit in the x1 direction, no units in the x2 direction, and if you do that, you will go up 3. The slope, rise over run, in the x1 direction is 3. So if you go 1 unit exclusively in the x1 direction, you go up 3. The rise in the x2 direction, and this is the x2 direction, is 2. And so these are the things that you need to write the parametric equation. I'll call it TP for tangent plane. It'll be a function of two variables, s and t. It'll be a point on, 0, 0, 8, plus s times the first direction, 1, 0, 3, plus t times the second direction, 0, 1, 2. And the range of this function will be the tangent plane that we're interested in, be this tangent plane. So in this case, the point on it is the point 0, 0, 8. That's this green point. And that lies exactly on, that lies on the tangent plane. It's got a slope in the x1 direction, points straight at you, but in that direction, the slope is 3. So this is sloped up by 3 in that direction. It's sloped away from you so you can't see it. I'll slope it down to -3 just to give you the idea. And in the x2 direction that's perpendicular, it's sloped 2. So there is that plane. And here is the x2 direction. Where are the other directions, which are directions of lines that are tangent to this surface, to Ohm, if you want? Where are those other directions? They are linear combinations of these red and blue vectors. So any linear combination of these two gives another direction of a line that is tangent to the surface at that green point. And those are the only directions. The span of these two directions gives the collection of all directions of lines which are tangent to the given surface at the given point. Okay, so how is this stuff used? Well, from here to here, these are used a lot in finding Cartesian equations whose graphs are tangents, or in finding parametric functions whose ranges are tangent to a given surface. Let's take a look at one. So let's take a surface, for example, surface of S and T. A surface has two variables, and maybe this is T cosine S, T sine S, and then T. So here, this will give a surface. It's a complicated surface. And let's find the tangent plane when T equals 1 and S equals 0. So the tangent plane, this is given parametrically. So we'll look at the tangent plane when T is 1 and S is 0. So the point on, plug and chug. If S is 0, the cosine of 0 is 1. T is 1, so you get 1. Sine of 0 is 0. So the point on is 1, 0, 1. And so now we want dir 1 and dir 2. How can we get these two directions from this? Well, this parametric function has, we can find its derivative with respect to t, and we can find its derivative with respect to s. So the derivative of SR of S and T with respect to S, for example, is equal to derivative of cosine is minus the sine. So T times minus the sine of S. Derivative of sine is cosine. And so this is T cosine S and 0. And now if we sub in S equals 0 and T equals 1, we will get the first direction. So take this point and sub it in, and it gives us the first direction. If we sub in S equals 0, the sine of 0 is 0, so the first coordinate is 0. If we plug in 0 for S here, we get 1. T is 1, so we get 1. And the last component is 0. So there is our first direction. To find the second direction, we want to do the same thing, but take the derivative with respect to t. And I'm going to erase this and do it above, so they're both on here at once. The derivative with respect to t is cosine S, sine S, 1. And now if we take this point, 1, 0, 1, and sub it in there, it will give us the second direction. So cosine of 0 is 1. Sine of 0 is 0. 1 is constant. So here are the two directions of the tangent plane at this point. So we can write the equation for the tangent plane, TP, of S and T is equal to the point on, 1, 0, 1, plus t times the first direction, 0, 1, 0, plus s times the second direction, 1, 0, 1. And you can combine these. The x coordinate is 1 plus 0 plus s. The second coordinate is 0 plus t plus 0. And the last coordinate is 1 plus 0 plus s. So here is the parametric equation for the plane tangent to this surface at the point where t is 1 and s is 0. Okay, so tangent planes via slopes, tangent planes via derivatives of functions, and we'll ask to do both, and we'll ask to plot the tangent plane together with the surface on the same plot, this sort of thing. One last thing. In the problems I've been giving you, there's the following situation that has happened, and that is I give you a curve. In this case, I think I gave you a straight line, but let's think of a curve. So I give you some space curve, r of t, and here's a picture of it. And I also give you a temperature distribution. Say the temperature distribution in space at x, y, z is 10 divided by 1 plus x squared plus 2y squared plus 3z squared. So at any given point in three-dimensional space, this will give you the temperature. And we have a moth, maybe this should be m of t. We have a moth flying through space. There he is. So at time equals 0, he might be here. So this is the moth of 0. At time equals 1, he's here, moth of 1. At time equal 2, here he's here. And I would like to know the temperature of the moth at each of these points. The temperature of the moth at each of these points. Moreover, I would like to know information about that temperature function. Is the temperature increasing or decreasing for the moth as he travels this path? So those are things I would like to find. So let's find temperature of moth as a function of time. So we want it in terms of the t variable. So I'm going to erase the moth picture here. What is this? Temperature of moth. Well, the terms in mathematics use this. You find the temperature of the moth at any time t. So the very terminology of composition of mappings, T of M of T, refers directly to the common language, temperature of moth, temperature of moth. And so the moth is a vector. It has an XYZ component. And how do you find this function? You plug the X from the moth formula in for X, the Y in for there, and the Z in for the Z there. That means you will only be left with the T variable, and that's what this is. Now, in general, if you wanted to find the derivative of a composition, this is called a chain rule. If this was a one-dimensional problem, you would take the derivative of temperature, you would evaluate at the moth, and then you would multiply by the derivative of what's inside. And there are several issues for us here. The derivative of temperature, first of all, has three components. It has three partial derivatives. The derivative with respect to x the derivative with respect to y, and the derivative with respect to z. So the total derivative has 3 components. This is a vector. M prime of t, m is also a vector quantity. It's the Moth formula. And so its derivative also is a vector. So the question is, what is this multiplication? I mean, if the chain rule formula is going to continue to be like this can't be regular multiplication of numbers. It has to be something else. So we'd like to know what this multiplication is for the chain rule. And I ask you a question about to see if you can figure out what this is in one particular case. So that's it for today. I got to go check on the little birdies. And I'll see you Friday.